Hello everyone, welcome to the course Mechanisms. I'm the instructor Wei-Jiun. So in this video we are going to learn some fundamentals of mechanisms. The goals for this lecture is to learn the definition of mechanisms and their components. When I say components, I mean the links and the joints. Don't worry too much about those terms, we will define them in this video. And we'll also learn how to calculate the mobility of 2D and also a few 3D mechanisms. We will mainly focus on the 2D part, but we'll still cover the 3D part a little bit. So kinematics. What's the definition of kinematics? Kinematic is basically the study of position and its time derivatives of certain mechanisms. So the time derivatives, of course, that includes the velocity and accelerations. And when I say position, velocity, and accelerations, I mean the linear motions, but there are also angular motions. So we'll also study the angular position, angular velocity, and angular accelerations of bodies. So take this mechanism, this 4-part mechanism, it will appear quite often in the future. Let's see the mechanism. So kinematics, what we will learn is, take this one as example. If we provide input here on this bar, we expect some motion will happen on this output link. So kinematics will help us to calculate if we input a known motion here, what would be the output motions. So that will include if I provide an omega here, we will use kinematic method to find, or we'll perform kinematic analysis to calculate the angular velocity of this bar. And we may also be interested in the position of certain point. So if I have a certain angular velocity, angular displacement, how this point is gonna move. So that's what we are gonna learn in kinematics. So this course will basically mainly focus on those position, velocity, and accelerations. And we mostly in this course we will focus on analysis, but allow me to introduce another word, synthesis. Well, let's take a look at analysis first. So for analysis, we use this 4-part mechanism as example again. For analysis is if we already know the mechanism. I mean, I know the geometry, I know the dimension of this mechanism. Then we use the kinematic analysis to calculate the motion of the links. So again, if I know the input here, I do the analysis to find out the motion of the output or the other links or other points. So if we do a problem in this way, that's called analysis. But what's synthesis? Yes. Synthesis is if we know a desired motion. So for example, I want a bar to move in this way. I want the bar to swing between two limits. I want this motion to happen. Then I need to design a certain mechanism that can perform this motion. So we define the desired motion first, and then we try to build the mechanism. So if a problem is this type of problem, we call it synthesis. Sorry. So synthesis is we know the motions, we find the mechanisms. Analysis is we know the mechanisms, then we find the motion. You can see they are reversed. Yeah. And in this course, we'll mainly focus on analysis. But in the can and follower part, it's more like a synthesis problem. So the definition of mechanism, I think we also mentioned this in the previous video. Let's just take a quick review. A mechanism transfers motions and mechanical work from the actuator to the output members. We use the 4-part mechanism again. Oops. So we give the input a certain motion, the output will perform another type of motion. So we transfer one type of motion into another type of motion. And of course, they also transfer the mechanical work. And also, a mechanism contains, basically two things. One is the joint, and one is the links. A joint you may also see in other textbook is called pairs. But anyway, pairs and joints, they basically means the same thing. So a joint is used to connect the components. So for example, this joint is connecting this bar and this bar. Yeah. And a link is a rich body. So, basically link, that's the link. And this one is also link. So, yeah. So link and joint, we use joint to connect links. Yes. So that's what the mechanism contains. So regarding link, let's see the definition of link. A link is a rich body that possesses at least two nodes that are points for attachment to other links. So links may look like this. It's a rich body. Rich body means these things cannot be deformed. It's rigid. And through our entire course, we only consider rich bodies. So all the links, they are not deformable. Yeah. Okay, back to this link. So this is the link. This one is a link with two nodes. We can also call it a binary link. That means it has two nodes. And for easy presentation, we usually draw the link in this way. Just a line with two circles. Yeah. That's easy for you to view it, for you to draw it. And there are also links with more joint. So for example, this ternary link, it has 3 nodes. Yeah. But its original shape would look a bit complicated. But when we draw it, we can draw in the simple way. We can just draw a triangle with 3 nodes. We can also draw in this way. Just pay attention. If you draw in this way, remember to put the dark triangle here. That means this bar don't draw it in this way. Try to fill a triangle here. That means these two bars, they are welded, so there's no relative motion between this link and this link. It's just a way to present the link. And you may also draw in this way. Yeah. But it may look a bit confused. Let me just explain this. I take these two as example. Just to clarify, these two, they are not the same, they are different. This one means there are two links, and with one revolute joint connected these two links together. So there are two links in this one. But for the bottom one, there's only one link. Yeah, there's only one. And this one, we put a small brick here. That means there is no relative motion between these two lines. So it's also similar to the triangle, but we just use a white block instead. That means it's welded. So the whole body belongs to the same link. And yeah, and this one has 3 nodes. Yeah. So you will see this type of schematic a lot in the future. So just remember these two, they represent 2 different type of links. Yeah. And the link may contain more nodes, so there are links with 4 nodes, or you can draw them in this way, very similar to the ternary link, so I'm not going to talk more about them. Okay, let's move to the next slide. And type of motions. A mechanism can perform certain motions, or you can say a joint can make the component perform certain motion. So we can categorize the motion into different types. Here I just categorize them into 3 types. It's simplified categorization, but let's just see. So the first one is just pure rotation. So for example, the 4-bar mechanism, they do the pure rotation, pure rotational motion to each other. If I use this R joint to connect these 2 bars, they do pure rotation. Well, this bar 3 is not going to have translation motion relatively to bar 2. So we call this pure rotation. Also, there are also pure translation, or we may call it prismatic motion. Is assume there's a slider sliding along this line. The slider, because it's like a block, so it cannot rotate. So it can only slide. It can only perform linear motion relatively to the ground. So this type of motions are pure translation, and we also call it a prismatic motion. And there are some more complex motions that might be a combination of rotation and translation. but we'll see more of them in the following slides. So motion, let's move to the another term, joint. A joint is a connection between only two links. Very important is only two links. Okay, so there are also, we can categorize a joint into two types of joint. One is called a lower pair, another is called higher pair. So what's a lower pair joint? Lower pair joint means a link and another link, when they contact, they are in surface contact. For example, I take this slider, for example, for 3D case. Suppose this slider is sliding on this surface, sliding maybe in any direction. What's the contact between this block and the surface? It's a surface contact. It's like you put a mouse on a surface. The whole surface is in contact. So if the joint is like this type of contact, we call it a lower pair joint. But what's a high? It should be higher pair. Sorry. What's a higher pair joint? A higher pair joint means the contact is only a line or a point. So imagine if I put a cylinder also on this surface, then what would be the contact condition between the cylinder and the surface? It will only be a line contact, right? Because only the very bottom of the cylinder will contact the surface. So the contact condition is only a line. If a contact is in this type, then we call it a higher pair joint. So that's the difference between a higher pair and lower pair joint. Let's see some more examples. So lower pair joint. Before we take a look of a lower pair joint, let's just define we mentioned before there are two types of mechanism we are going to discuss in this course, and we'll mainly focus on the 2D case. The 2D case is also called a 2D mechanism is also called a planar mechanism, and for 3D one is also called a spatial. So for planar mechanisms, what type of motion or what variable does a planar mechanism have? It has several variables, which is x, y, and theta. What does that mean? Suppose I have this pen is moving on a plane, so planar mechanism or planar motion. How this pen is gonna move? It can move in the x direction, it can move in the y direction, and it can also rotate. So three variables here, x and y and theta z, because it's rotating about the z-axis. Z is inside the surface. Yeah. So x direction, y direction, and the rotation. So that's the motion a planar mechanism can do. But what about a spatial one? Spatial one, well, you can move in more direction. You can move x and y and z direction. You can also rotate about the three directions. So there are 6 variables for a spatial mechanism, but only 3 variables for planar mechanism or planar link. Okay, so let's take a look of the lower pair joints. And well, there are many informations here. Let's take a look at the first one, the revolute joint. It has many different names. It may also be called a hinge, a pin, or a turning pair. Anyway, we'll call it a revolute joint, or to the abbreviation is called R joint. We take the R, we call it R joint. So in the future, I will just call it a R joint. That means the revolute joint. Revolute joint means it's going to constrain the two links with only one type of motion, which is a rotational motion. So, for example, this one, if I call this link 2 and link 3, they can only do a relative rotational motion, which is a theta. Yeah. So in the panel representation, we use a small circle to present the revolute joint. So there's a link here, and with this joint to connect these two links. And the second one we are going to talk about is a prismatic joint, or this is also called slider or slider pair. We use a symbol to abbreviate this. So we'll also call it a P joint. A P joint means the two components, they only have relative linear motion in one direction. So like this one, you can only move in this direction along this line. Yep. Too messy. Along this line. Yes. Or for this symbolic representation, it's moving along this line. Yeah. And both of the R joint and P joint, they only have 1 degree of freedom. That means it can only move x, y, theta. It can only move one of them. So for this one, I will call it can only move in the x direction. For rotational one, it can only move in the theta direction. So only 1 degree of freedom. Okay, so let's take a look of the third one. It's a screw joint, or it's also called helical joint, helical pair. And this only happens in 3D mechanisms, so you can see there's no planar symbol here. So what does a screw joint do? A screw joint, well, is basically a screw and a nut. When this nut rotates, this nut can rotate on this screw, but when you rotate, you will also move in the actual direction, right? If you do the counterclockwise, you will move in one direction. If you do it clockwise, you will move in the opposite direction. So anyway, when you rotate, you only move. It's not only rotating; it's only the linear motion. But the important thing is the rotational motion and the linear motion of this joint. They are dependent. So that means if I rotate like one round, it will also move with certain distance. So if I rotate theta, it will move with s. If I rotate 2 theta, it will move 2s. So basically, the linear motion and rotational motion, they have certain relationship. They are not independent to each other. So when we talk about the degree of freedom of this joint, although there are 2 variables within this joint, a linear variable and a rotational variable, but they are dependent to each other. So there is only one degree of freedom. You change the theta, the S will also change correspondingly. So there's only one degree of freedom in this case, in this joint. And another example, another joint is a cylindrical joint. A cylindrical joint will look a bit similar to the screw joint, but there's no screw. So in this case, in this joint, the theta and the S, they are independent. Yeah, I can move freely along the S direction. I can rotate freely along the theta direction. They are not dependent. So for this cylindrical joint, there are two degrees of freedoms, S and theta. They are independent variables to each other. Okay, and again, there's no planar symbols for all the joint in this page, because they only happen in the 3D case. And also a spherical joint. Spherical joint is also called ball joint. You probably have seen this before, so you can rotate freely within the cover, or within the shell. Yes. Okay, so rotate, and you can rotate in any direction. So it has 3 degrees of freedom, but all about the rotational motion, the rotation along different axes. And there's a planar joint, so it's basically a plane, a brick sliding on the surface. So it also has 3 degrees of freedom, the x direction, y direction of a linear motion, and also it can rotate along the z direction. So the above, they are all the lower pair joint. So you may notice they all have surface contact. So for this ball joint, is all the surface of the ball is contacting the surface of the shell. Yeah, and the others, they are the same. They are all in surface contact. Okay, so the higher pair joint should be higher. Higher pair joint. Higher pair joint, well, there are also many types of higher pair joint. Well, let's start with the first one, the cylindrical roller. So it looks like it has 2 degrees of freedom, but it's not. Okay, so a roller means the friction is very strong here. So there's no slipping. The roller will not slip on the surface. So it means when it rolls, it will also do the linear motion. Yeah, I cannot move in this way because the friction is very strong. So I can only move in this way. Yeah. So very similar to the helical joint, or the S and the theta, they are dependent to each other. So this one is 1 degree of freedom joint. And the second one is a cam pair. Cam pair is similar to the cylindrical roller, but it allowed the sliding. So you can slide and you can rotate. So there are 2 degrees of freedom. And well, so these two can happen in 2D and 3D case. You will be able to see them in both 3D and 2D mechanisms. And the following 3, they are only in 3D mechanisms. So for rolling ball, well, it's very similar to the roller, but you can roll in 3 directions. but again, there's no sleeping. So 3 degrees of freedom for this rolling ball. And ball is cylinder. Well, it allowed the sliding. Yeah. So anyway, so it can rotate within the tube, but it can also move along this S direction. So it has one extra. It has one more movement than the previous one. So 4 degrees of freedom. And there's also the final one, a spatial point contact. That means the object is contact. The object contact a surface, and it can move in either way, and you can also rotate in any direction. But the only constraint in this joint is you always need to make contact between these 2 components. So you cannot leave my fist out of this surface. They must always be in contact. So anyway, this one has 5 degrees of freedom. 5 degrees of freedom. Okay. Just to pay attention, those higher pair joints, they are either line contact or point contact. You can see the ball, the rolling ball, it has only one contact point. Yeah, it's the very bottom of a ball is in contact with the surface. Yeah, and others, well, this is linear. The first one is line contact, line, point. This one is also line. This point contact, and line contact. So they are all higher pair joint. Okay. And here comes the compound joint. Compound joint is it works like a certain joint, but if you take a look inside of this joint, it's not the original joint, but it sounds a bit complicated. So, for example, a ball bearing. A ball bearing, what type of motion is going to perform? A ball bearing works like an R joint. It works like an R joint, but it's a bit different from the original R joint. If we take a look of the interior of the ball bearing, it's like this. We use the ball and we use 2 rings, and they are both within the 2 rings. So the 2 rings, they can do a relative revolute motion. Yeah. So it works like an R joint. But remember the R joint we introduced previously, they contact in surface. But this is not good, because if you these 2 components, they contact in surface, it's going to generate a lot of friction. So it's not going to rotate smoothly. But with this ball bearing, it's not the regular R joint, but it works like an R joint. It's basically use ball joint to assemble a new R joint. Yeah, so we call this type of joint a compound joint. Compound joint. Sorry. Yeah. So another example is a universal joint. Is we use 2 R joint to make the joint can do universal rotational motion. So yeah, so right now this joint has 2 degrees of freedoms because we combined 2 joints together to make a new joint. So this another type of compound joint. And another example we've seen quite often is a roller guide or roller slider. The purpose of this one is to mimic a P-joint. But if you remember the P-joint we mentioned in the lower pair joint, is in surface contact. But if we install some roller here, it will still work. It still works like an P-joint, but with lower friction. Yeah, because now it has a roller, has a smaller contact area. Yeah. So those compound joints, they are used to mimic certain type of joints, and they can achieve better performance. Yep. Okay, and there's also an we call it kinematically equivalent joints. What does this mean? It means this one and the left one and the right one, they perform the same purpose. They serve the same purpose. So for this one, for the left one, we can see the bar 3 or link 3. What's a relative motion between these two? It can rotate. Well, suppose this one is fixed. I think it's easier for you to think. The bar 3 can rotate. It can move. It can also move along this slot. So it can move in this direction. It can also do the revolute motion. But we can, instead of using this one, we can use this one instead, the right one. But the right one has one more component. It has a new link 4. But when you take a look of the link 3 and link 2, you will find their relative motion is the same as the one in the left-hand one. The bar 3 can also do a revolute motion, and it can also slide along this horizontal line. So because in these two cases, when we look at the link 2 and link 3, their relative motions are the same. So we will call these two joints. They are kinematically equivalent. So yeah, you may use this one to replace this one. They can replace each other. Depends on your applications. Yeah. And kinematically they are the same. So revolute joints we've mentioned a lot. Revolute joint is to make 2 links. They perform relative revolute motions. Or we've said this a lot, so I'm just going to quickly go through them. And this one is the 4-bar mechanism we use several times. So this mechanism we also call it a 4R linkage. 4R means it has 4 revolute joint, 4R joint. So this one is called RRRR linkage, or called 4R. Well, and here's another example. a linkage formed by revolute joins only. And prismatic joint, the one we see most often is the crank slider. And so between link 1 and link 4, there's a joint connecting link 1 and link 4, which is the P joint. So bar 4, or link 4, it can move along the line on bar 1. Yeah. So it's do a sliding motion. And this one is also called an RRRP, or 3R1P linkage. It means there's R joint, R joint, R joint, and a P joint. Yeah. And also in this example, this more complicated linkage, there's also a P joint here, doing the sliding motion. And the Canon follower. Yeah. So for these mechanisms, there's also a joint. Let's call this bar 2, bar 3, bar 1. Okay, there are 3 components. Or just for your information. Usually through this entire course, we always call the grounded link 1. So we assign number 1 to the grounded link. Yeah. And we usually call the input link 2. Yeah. It's not always the case, but most of the time we prefer to use them in this way. Yeah. So right now, this cam and follower mechanism, this one is cam. So we use a cam tool as a driver, and this follower, bar 3, link 3, is driven. And so there's a joint here between bar 2 and bar 3, or link 2 and link 3. The joint is called cam joint, or cam joint is a combination of rolling and sliding. So that means this link 2, it has relative rolling and sliding motions on the bar 3. Yeah. And of course, between link 1 and link 2, there's R joint. Link 1 and link 3, there's R joint here. Okay, so another new term, that's a chain. Well, we won't use this term quite often, but just to give you an idea what does a chain mean when you see this term in the textbook. A chain is an assembly of connected links. So for example, we have link 2, 3, 4, 5. So this whole assembly of the connected links, we call this a chain. Yeah, so that's just a definition. An assembly of connected links is called a chain. And another one is a closed chain. For closed chain, that means every link is connected to at least 2 other links. So for the top one, this one, it's not a closed chain. But we don't call it open chain, we just call it a chain. But for closed chain, it says every link is connected to at least 2 other links. So let me assign a number to them first. So say every link is connected to at least 2 other links. We see if this is true in the bottom mechanism. So say link 1 is connected to link 2 with the R joint, and also connected to link 4 with a P joint. How about link 2? Link 2 is connected to link 3 with R joint and link 1 to R joint. Link 3 connect to link 2 with R joint and connected to link 4 with R joint. And link 4 is connected to link 3 and link 1. Yeah. So every link is connected to at least 2 other links. So this one is a closed chain. And in the entire course, we mainly focus on the closed chain. Basically, a closed chain is a mechanism we are interested in. Okay, so some new terms. And first one is the frame and base. So, frame and base means the link that is fixed and has 0 degrees of freedom. So, for example, the ground in a slider crank. So, in a 4-bar mechanism, we always need to fix one link, which is the bottom one. So the frame or the base is basically this one. It is fixed and it has no degree of freedom. It is unable to move. Yeah, and in the schematic drawing, you can draw in this way or this one. Yeah. And the frame or the base is usually designated as link 1. Yeah, so it's link 1, 2, 3, 4. So mechanism is a closed chain with one link fixed. Yes? Okay. Okay, so this is the example. We fix the track. Okay. Alright, so a mechanism is a closed chain with one link fixed. So this is a mechanism and this is also a mechanism. They both have one link fixed. And one thing is not mentioned here is all the fixed link are considered as a single link. So for example, here we have a fixed base here, another fixed base here. They are all belong to link 1. Well, they are the same one. We consider them as a single link.